Hello everyone and welcome to my channel. In the second video on surface integrals, we will be beginning with the evaluation of surface integrals of vector field. Before that, if you have not seen the first video in this, I want you to go back and see the first video. I have attached the link in the description and also at the top right corner. So to begin with surface integrals of vector field, let us quickly recall what is a vector field. A vector field is a function usually denoted by capital F. It is going to be from Rn to Rm, where m and n are natural numbers with the constraint that m must be greater than 1. So basically speaking, a vector field for every n tuple returns a vector of m tuple in Rm. Now moving on to the definition of surface integrals of vector field, we are going to deal with functions or vector field from R3 to R3. And we will also be given a surface in R3. This surface would be parameterized by a function gamma of two variables, say u and v, and it is going to be given by x of uv, y of uv, and z of uv. And let's say u comma v belongs to T, which is a domain in R2. So we will be dealing with surface integrals of the vector field f over S, and it is denoted like this. To evaluate this, we need to do double integral. The integral on the right side is a double integral. So we will be finding out the image of the vector field on the parameterization that is given by gamma of uv. So we want f applied on gamma of uv, and we will take the dot product of this with the fundamental vector product or the normal, which is given by cross product of gamma partial derivative with respect to u into gamma partial derivative with respect to v, and we will be integrating this with respect to du dv or dv du depending on the type of region T is going to be, whether it is going to be type 1 or type 2. So as discussed in earlier video, we have seen that there is no specific notation for surface integrals. So we need to understand that the double integral written on the left hand side is a surface integral, while the one on the right is a double integral. Now let's try and utilize this formula in solving the first problem, wherein we are given a vector field f as image 18z, comma negative 12, comma 3y, and S is the surface which is given by 2x plus 3y plus 6z equal to 12 in the first octave. So to begin solving this, we first got to parameterize the needed surface. So as you can see, the surface is given by the plane equation 2x plus 3y plus 6z equal to 12, and it is in the first octant. So first octant indicates that all the three variables are going to be positive. And let me just write down the function as well. So we have f of xyz equal to 18z, negative 12, 3y. So to parameterize this in vector spaces, you might have studied that this is in R3 and a plane has dimensions 2. So over here I can rewrite this equation either in terms of x and y, or in terms of y and z, or in terms of x and z. Let me just rewrite this equation in terms of z. So from here I can say that z is equal to 12 minus 2x minus 3y over 6. So what we can do in this case is, instead of introducing new variables u and v for parameterization, we can say that the surface S is parameterized as gamma of xy, where the x ordinate is x, the y ordinate is y, and the z ordinate is given by this expression. So we can replace the z ordinate by 12 minus 2x minus 3y upon 6. And we got to give the domain for x and y because that will be the region of double integration. So currently I'll say that x comma y belongs to T. To find the domain T required for the double integral, we need to look out at this surface S in R3 and its corresponding projection in the xy plane, since we have specified xy to be the variables for double integration. So first we will be seeing the surface in R3, followed by its projection from the z axis in the xy plane. So this is the surface S in R3. Now it represents a triangular plane with one of the vertex on the z axis, and that vertex is going to be when you put x and y as 0 and we substitute in this equation of the plane, we get that 6z is going to be 12, and that gives us that z is going to be 2. Likewise, for the coordinate on y-axis, we got to substitute x and y as 0, and when we do that, we get y equals 4. And for the x-axis, you need to substitute y and z as 0, so this will give us that x coordinate is 6. So this is the surface. It's kind of a triangular plane coming down from the positive z axis up to the xy plane. Now what we need is we need the projection t in R2 or on the xy plane. So for that, what we do is we will be looking up right from the positive z axis. So this is going to be our point of view. We'll be looking over here, and what we will be seeing is we'll be seeing this triangular plane, and this triangle is formed in the xy plane. So the vertex 0 0 2, it will drop down to the origin 0 comma 0, and all these things in the xy plane, so 6 comma 0 6 0 0 will be mapped to 6 0, while 0 4 0 will be mapped to 0 comma 4, and 0 0 2 is mapped to the origin. And we can join these 2 points, and this is the region T of integration, of double integration. Now it's both type 1 and type 2. So once you realize that it is type 1 or type 2, you can set the terms for writing down the limits. So let us consider that this is a type 1 region, and for type 1 region we are going to take a vertical line for reference. The vertical line enters the region at the x-axis, and x-axis is equation y equals 0. So the lower limit for y is 0, while this vertical line exits the region at this oblique line. The equation of this line, since it is formed by the surface in the xy plane, which means that I should be solving 2x plus 3y plus 6z equal to 12 and z equal to 0. And once we do that, we get the equation to be 2x plus 3y equals to 12. So the equation of this line is 2x plus 3y equal to 12. So the upper limit of y is going to be 12 minus 2x divided by 3. And this reference line can move from this, which is your y-axis. So the lower limit is going to be 0 for x, while it could maximum reach here, and here you can see the x takes value as 6, so the upper limit of x is going to be 6. So this is the region T, which will give us the required limit for integration. So at the moment we have the parameterization gamma. We also need the fundamental vector product. So let us go ahead and evaluate the fundamental vector product. So to evaluate the fundamental vector product, we need gamma partial derivative with respect to x, and it is going to be 1 0, and we will get here negative 2 over 6, which results up to 1 0 negative 1 over 3. And we need gamma partial derivative with y, which is going to be 0 1 and negative 3 over 6, which is equal to 0 1 negative half. For the next part, we are going to take the vector product or the cross product of these two. So for that, we will take help of the determinant. We'll have first row as the unit vectors I, j, k. The second row will be gamma x, which is 1 0 negative 1 by 3. The third row is gamma y, which will be 0 1 and negative half. So taking the determinant, we will get the I component to be 1 by 3 minus j, it is going to be negative half, and lastly the k component, which is going to be 1. So thus the normal or the fundamental vector product is 1 by 3, half and 1. The surface integral f ds over s By definition, this is going to be double integral over t f applied on gamma of xy, the dot product taken with the fundamental vector product, which is gamma x cross gamma y. And since we have said that t is type 1 region, so the order of integration is going to be dy dx. Now writing down the limits for x, it is 0 up to 6. The limits for y is from 0 up to 12 minus 2x over 3. Now we got to apply f on gamma of xy. So f applied on gamma of xy, it is going to be f applied on x, y, 12 minus 2x minus 3y over 6. And as per the definition of f, this is going to be, we have f here. So this is going to be 18z. That means the z component needs to be multiplied by 18. Make a note that we have 6 in the denominator, so we can reduce the 18 to 3. So we will get 36 minus 6x minus 9y. The second component is a constant, that's negative 12, while the third component is going to be 3 times of y, so that remains as it is. So this is the function or the vector field we are going to consider. So we have got the vector field, the image of the vector field on the surface of on the parametric equation, followed by the dot product taken with the normal, which is 1 by 3, 1 by 2, 1, and dy dx. Now let us simplify this. We need to take the first coordinate from here and the first ordinate from here, since it's a dot product, so that is going to be 12 minus 2x minus 3y plus. Then we need to take the second ordinate, that's negative 12 times half, so that's going to be negative 6, and the last component is going to be 3y. So you can see that we can get rid of the 3y, and 12 minus 6 reduces to 6. So this reduces to a very simple double integral, where the integrand is going to be 6 minus 2x. And I'll leave the rest part up to you. So that's how you surface integrate a vector field. Now there are some more problems available here. Now in certain cases, if you look like question number 3, the function is given and the parameterization itself has been given. So these are very easy to do problems. If you will look at question number 4, in question number 4, we are given that S is the parabolic cylinder y equals x square, which is bounded by, there is a range of x which is given, and also there is a range of z. So these give us the hint that what parameterization we can take for the surface S. So for problem number 4, the parameterization that we are going to take will be dependent on x and z. And since it is x comma z, so your x will remain x. Now, if you will look that we have the surface equation to be y equals x4. So instead of writing y, we can write the second ordinate as x square. And then the z ordinate remains z. And the limits of x and z, they are already given to us. So it is going to be Cartesian product of closed interval 0, 3 to 0, comma 2 closed interval. So that's all in this video. I hope this video helps you. In the successive classes, we are going to deal with how we can use these formulae to evaluate areas, and followed by Stokes theorem and divergence theorem. Thank you so much.